before we before we get into the into chapter 7, I want to share the syllabus and show you the correction I made. There, my screen is sharing. That's good. Okay. The only point I want to make here is in the syllabus. This is the corrected version, so I'll have to tell you what was wrong with it before. The notice here 7.1 to 7.8 was just on today, and 7.9, 7.13 was for next Friday. But that pushed chapter 8 on the same day as the review. We can't do that. All right, so we're going to cover chapter 7 today, chapter 8 next week with a lab, Boyle's Law. And then we'll have all of March 31st to do review and a second lab on molar mass by freezing point depression. I'll hand that one out next week. Okay, that's all I wanted to show you there. So let's fight the share monster again. Okay, let's turn this into a slideshow, if it'll let me. Go down here and do it then. There we go. All right. I want to get my participants. There we are. So I can at least see myself. You may wonder what these little boxes are. These are the places on the video that are washed out with glare from the lights. So I boxed them out so I won't write over them or erase them. So we'll have to work around those. I've noticed on previous recordings that anything that comes across these areas is washed out and I can't fix it. So I'm not even going to write in those areas. All right. Chapter 7, gases, liquids, and solids. We've got a lot of topics to cover, but we should be able to get through with it because we don't have a lab today. All right, the authors of your text start off with kinetic molecular theory of matter. And that's the general topic, but we need some introduction before we get into the theory itself. A reminder about physical properties. When we discuss solids, liquids, and gases, we define them with these first two, volume and shape. So volume and shape, what we mean here is for the gases, there's indefinite volume. In other words, the gas occupies the space that is given, and it'll expand or contract based on that. And it also has an indefinite shape. It will assume the shape of the container. Liquids have a definite volume, but they have an indefinite shape. So you do need a container for the liquid, but it doesn't have to be completely enclosed. It can be something like a beaker or a flask. But the volume will always be the same at a given temperature, but it will the liquid will conform itself to the shape of the container. And then solids, of course, they have a definite shape and a definite volume. They can maintain their own shape above their melting point, of course. So once you melt a solid, now it's in a different phase. It's in a liquid. And if you boil a liquid, now it's in a gas. So we can transform solids, liquids, and gases among each other for a specific substance. Other descriptions of physical properties of matter include density. Now, density is going to be an intensive property. That is, once you define the density for a substance, it doesn't matter how much of it you have, the density will be the same. Compressibility, we know that gases are very compressible. Liquids and solids are generally considered to be incompressible, but liquids we've discovered are, to a greater or lesser extent depending on the substance, they have some compressibility. We know that because samples have been taken of water at 2 miles down in the ocean and measured the density down there, and the density is much greater. It's higher. So water is compressible, we know that much. But for our purposes, at normal conditions of temperature and pressure, we can consider liquids as incompressible. Thermal expansion. When you heat something up, it's going to expand. Now, when you heat up a gas, it expands a lot. When you heat up a liquid, it expands a little bit. And when you heat up a solid, it will also expand. That's a physical characteristic. The identity of the substance has not changed. And all these properties can be explained using the kinetic molecular theory, which we're going to get to eventually. So all compressibility says is that the volume changes under different pressures. And it can be quantified. We're going to do that, especially with gases. And with the lab that we have next week, we're going to quantify it in a special way, which we'll discuss later on. When we get to gas laws, I'll talk about that a little more. Now, thermal expansion can be expressed, especially for solids. It can be a linear expansion. So the substance is like a bar of whatever, the solid or the metal. And if we increase the temperature, if we change the temperature this much, it may expand by that much. Oh, we got a visitor. Okay. And we express the percent. Well, actually, it's a coefficient of expansion. So it won't be percent. It'll be a fractional change. So the fractional change of this, based on that model, it's a ratio of this distance here to what it was relative to a change in temperature. So we can quantify that also. That's linear expansion. You can have area expansion defined, or you can have volume expansion. But it's a similar approach. What was the original volume, and what fraction of that original was the increase responsible for a change in temperature? Come on. Oops. I lost my, is it up here? No. Okay, I can't see anybody now. I got to it before. Let's try this. There it is. All right. So this is just this comes straight out of your textbook, and it's a composite table of the discussions that we've had about these different physical properties of solids, liquids, and gases. Okay, now to the kinetic molecular theory, which allows us to explain these chemical properties and the changes that they may reference. First of all, these are all considered postulates. So the first one is that matter is composed of tiny particles, right? I mean, that's nothing new. We knew that already. As a student in this class, we knew that up to this point. They could be atoms, they could be molecules, they could be ions. For instance, table salt, right? Those tiny particles are ions. And each of the tiny particles have a definite size that does not change. Right? So we're going to consider these tiny particles as just little balls for the purpose of argument. These tiny particles are in constant motion. So they're always moving in some form or fashion. Now, if it's a gas, they're moving in a straight line until they smack into somebody. If they're solids, then they're just vibrating. If they're liquids, then they're vibrating because they're moving past one another. So as you go from a solid to a liquid to a gas, you get more of the linear transformation of their motion. And we can express their kinetic energy. If they're moving, we can express their kinetic energy in terms of this equation, 1/2 mv squared. So if we know the mass of the particle and how fast it's moving, we can calculate its kinetic energy. Now, particles interact with one another. This is one that I generally don't include in the theory, but since your book does, I'm going to stick with them. Particles interact. That's the nature of that interaction. That determines whether it's a solid, liquid, or gas. The basic type of interaction, the ideal interaction that we normally discuss, is that these particles are like billiard balls and they just bounce off one another. There's no attraction or repulsion involved. But in fact, we do know that most substances are not ideal and that they will interact with one another. They will attract, usually. Sometimes they will repel. It depends on how they approach one another. We've talked about dipoles, right? If you have two molecules approaching one another and they strike one another with their negative sides, then they'll repel. So this kinetic energy that we discussed earlier can be opposed by potential energy. And that is, potential energy is any stored energy. It's not realized yet. It may result by position, right? If you talk about large masses of things, you can say, all right, if I stand on the roof of this building, I have more potential energy than I do if I'm in the parking lot. And that's relative to the object that's creating the gravitational field, which is the Earth. And you can get that energy back. You can convert that potential energy of position into kinetic energy of motion. All I have to do is jump off the building. And right before I hit the ground, I will have all the kinetic energy that was stored in my potential will be available to me. Of course, once I hit the ground, then that kinetic energy is reconverted into potential energy, such as broken bones and heat. You can also get potential energies of certain conditions, like, for instance, if I take, if I take this rubber band and I stretch it, I'm storing potential energy in that stretched rubber band. You can do that with a stretching force or with a compression force, and you can store energy in a substance. That's physical storage of energy. You can also store energy by chemical means in the composition. For instance, nitroglycerin. Right? Nitroglycerin has a lot of energy stored in the bonds. And all you have to do is just disturb it a little bit, and it'll release all that energy in a big hurry. So those are different types of potential energy. One that I left out, electrostatic interaction. An attraction or repulsion can be a form of stored energy. In other words, it's easier to show with magnets. If you take two magnets that have north and south pole, and you bring the south ends together, there's going to be a repulsive force. And it's related to distance. In other words, the farther away, the less the force. So the closer you get it, the more force you have to add, more energy you must expend to get those together. And you've stored energy in that magnetic field. This works with electrostatics too. If you have a molecule that's negative one side and this one's negative on one side, then the same thing works. If you push them together, then you're going to store energy in that repulsive force. Or if they're attracted to one another and you pull them apart, you're expending energy and storing that energy in that electrical field or magnetic field, as the case may be. And we might also add that on the molecular scale, these attractive or repulsive forces are not necessarily permanent. They can be temporary. All right, that was third point. Wonder why they're going back to, this ought to be buried in 2, kinetic energy due to velocity of particle. Oh, I see they're drawing a parallel between kinetic energy and temperature. Temperature is a measure of the average kinetic energy of all the particles in the substance. So as the temperature goes up, their kinetic energy increases. When these particles collide, they transfer energy to one another by elastic collisions. All right, so the transfer of energy occurs. Transfer of energy occurs by collisions. And these collisions are considered to be elastic. That is, all the kinetic energy that both particles have as they approach is the same amount of energy that they both have when they leave. Now, they may transfer, this one may be moving faster and transfer energy to that one, but the total amount of kinetic energy of the two particles is the same before and after. That's kinetic energy, elastic collision. All right. So what we're going to try to do is explain the differences between or among solids, liquids, and gases based upon a battle, so to speak, between kinetic energy and potential energy. Okay, kinetic energy. We characterize kinetic energy as disruptive. And potential energy, then, of course, I left out my L. Potential energy is cohesive. So the battle is between, if you have enough kinetic energy, it'll overcome all the cohesive forces and the particles will be more independent, further apart. Now we're talking about gases. Whereas if the cohesive forces are the majority, then they win and hold the atoms, the particles together, and now we're talking about a solid. And if they're roughly balanced, we're talking about a liquid. So that's where we're headed with this. The battle between disruptive and cohesive forces determines whether we have a solid, liquid, or a gas. Okay. So we mentioned that solids have a dominant force here. Excuse me, that's not right. The dominant force is here, cohesive forces. Whereas, maybe I should say this. That's not quite correct. This one is bigger than that one. There we go. Liquids are about equal, and gases are the opposite of solids. Disruptive forces exceed cohesive forces. And this slide also makes the point that with stronger cohesive forces, the particles are closer together. And they tend to fix themselves in positions. So if they're positioned, where their position in space is not moving, then the solid tends to maintain its own shape. That's just a picture of what they might look like. Now, the particles still have kinetic energy, right? We haven't done away with kinetic energy. It's just that it's small, and it's not a linear translation to a great extent. It's more like a vibration. So they are moving back and forth. And if we, and because the particles are so close together, they tend to give us a higher density. Remember, the formula for density is mass per unit volume. So if we decrease the volume by bringing the particles closer together, then the density goes up. And they're not very compressible either. The reason they're not compressible is because the particles are so close together, there's no room for compression. We can't decrease the volume any further in a solid because they're right up against each other. Their thermal expansion is not that great either. As we increase the temperature, they will start to vibrate more, which makes them expand some. But we're not adding a lot of volume to the object as we increase the temperature. They're vibrating faster, but they're not adding a lot of volume. They're adding some, but not a lot. And the reason that they're not adding volume is because these cohesive forces are still strong enough to hold them in position. Liquids, on the other hand, have relatively equal distribution between kinetic and potential energy. The disruptive and cohesive forces are balanced. They're still relatively near to one another, but the kinetic energy has increased to the point where they can move past one another relatively easily. We still get the attractive forces, the cohesive forces, but the kinetic energy is such that they're not now just vibrating, they're moving past one another. But they're still very close together, which means they still have a definite volume. But because they're not locked into a physical orientation, they don't have a definite shape. And this is a representation of what they would look like. Just randomly assorted particles. And they have to have a container to maintain their shape. The cohesive forces are still strong enough to restrict particles' movement within that volume, but they're not strong enough to prevent the particles from moving over one another. And they're only limited by the container's shape. They still have a relatively high density. As compared to solids, the density is maybe a little bit less, right? So we've increased the volume some, which decreases the density, but not much. Their densities are very close to one another. And for some solids, the solid is less dense than the liquid. That's kind of rare. It happens with water because of the way water forms a crystal structure. I've drawn that for you before, haven't I? Okay. Okay. They're not very compressible. Like I said before, you can squeeze them together, but it takes a lot of pressure. Like, I don't know how much pressure that would be. 2 miles down, 5,280 feet. Okay, that's 10,560 feet. And you get an atmosphere for every 33 feet. So that's 320 atmospheres at 2 miles down. So it takes a lot of pressure to compress liquids. They also have a very small thermal expansion. That's why in the laboratory, when we have aqueous solutions and we're bringing them to a definite volume inside a volumetric flask like this right here, we try to be extra careful about the heats of reaction or heats of solution. If we put something into solution and it heats up and we bring it to this volume, then when it reaches room temperature, the volume will drop. Or if it's cold, if it cools down when we make the solution, then we bring it to this, then the volume will increase. And it's noticeable. I mean, it's measurable. So, but if the temperature is relatively close, within a few degrees, a couple of degrees, plus or minus the calibration temperature for the glassware, then you can usually ignore any effect of temperature on the thermal expansion of the liquid. Gases. Okay, now we're talking about gases have very high disruptive forces and low cohesive forces. And this is a balancing act. In fact, for most gases, we consider the cohesive forces to be almost zero. And this only works for higher temperatures. And when I say high temperatures, I mean relative to Kelvin, right? Relative to 0 K, what is room temperature? Well, it's 293 or 298. Yeah, I guess it's 298. Okay, so that's high temperature. So high temperature room temperature is high temperature. And under those conditions, the cohesive forces are virtually zero. So the particles move independently of each other. They have a very high kinetic energy. I don't know, did we do it in this class where we calculated the velocity, average velocity of particles? Okay, I must have done that in a different class. But you can do that. And when you do, very often the molecules in a gas are moving at or above the speed of sound. That's from one impact to the next, which is not very far in our world. Like, it wouldn't be that far. It'd be right less than a hair's breadth. Because even in gases, there are lots of atoms, molecules in a small space. There's just not as much of the gases. The size of the particles relative to the size of the space they occupy is very small. So most of gases are empty space. Okay. Another reason that the cohesive forces are relatively small for a gas is because they're moving so fast. When they hit one another, they're not in contact for very long. And the amount of energy that they have in each of the particles and they transfer between one another is so huge that it's sufficient to overcome any cohesive forces. They have very, very low density. Right. Rule of thumb. If you take a liquid and heat it to make a gas, the change in volume is about 1,000 times. Now that varies all over the place, but that's roughly a change of 1,000 times the volume of a gas versus the liquid from which it's formed. So they have very low density. They have very large compressibility, and this is due to the fact that there's so much space between them. But they will fight back. Right? If you increase, you've got to increase the pressure in order to compress the gas. And that pressure is opposed by the molecules inside the gas banging against your plunger. So as you compress them, as you decrease the volume from, say, here to here, you've got the same number of molecules in either space, but when you put them in a smaller volume, you have many more impacts per cubic centimeter or per square centimeter on your plunger, is why the increase in pressure is required. They have moderate thermal expansion. We're going to talk about that a little later when we get to Charles' law. Charles' law relates volume change to temperature change. Okay. All right. So now we're going to get to the gas laws. Remember, the difference between a law and a theory is that a theory tries to explain why. That's why the kinetic molecular theory is so useful, to explaining what the difference, how we explain the difference between solids, liquids, and gases. But laws, in fact, gas laws came before any of the theories. And a law simply explains what happens, not why, just what happens. So it's more limited in its application. So if you step outside the conditions that are defined by the law, then the law doesn't work anymore. Now, in order to describe a gas completely, in physical terms, we need 4 terms. We need to know quantitatively its volume. its pressure, its temperature, and how much of it there is. That little n means number of moles. We defined moles, didn't we? Yeah, calculations. Okay, just checking. So these values, once you have these values, you can completely describe the physical, the conditions, the behavior of a gas. Now we need some we need to standardize these terms so that if I do an experiment and I list these values for my gas, then somebody on the other side of the planet, when they see my data, they will understand what I mean. So pressure, we'll start with pressure. Pressure is equal to a force per unit area. So in that respect, pressure is an intensive property. It measures an intensive property, force per unit area. Now, historically speaking, pressure has many different ways of being expressed. There's one standard way, which is called the Pascal. And the utility of the Pascal is that it is interconvertible with all the other SI units. It's a derived unit, in fact. It's 1 Newton per square meter. And the Newton's a derived unit too, so you get a derived within a derived. But we're not going to use Pascal. We find it more convenient to use some other units of measure. In fact, we're going to use atmosphere. All right, 1 atmosphere is simply the pressure that is exerted on any gauge or your body at sea level and room temperature. But we have interconversions also available. 1 atmosphere can also be 760 millimeters of mercury. Now, that probably won't mean anything to you because we haven't defined what that means. That's based on the barometer. We're going to describe the barometer in a minute or two. This is also 14.7 pounds per square inch. Okay. This was the first one I ever learned in school. 14.7 pounds per square inch, 1 atmosphere. 760 millimeters of mercury is also 760 torr. And torr is a unit that was created to honor the inventor of the barometer, Torricelli. Let's see. So the only one of those that contains the units of force per unit area is 14 pounds per square inch. Now, SI units, kilogram per square meter, that's not strictly speaking true. A kilogram is a measure of mass. Square meters, yeah, that's area. But newtons per square meter, that's the SI, standard unit for pressure. I described this a little earlier. Why do we have field pressure, or why can we measure pressure in a gas container? Right, we have a gas confined in here. So we stick a gauge in it, right? And we can measure the pressure. So the only reason we can measure pressure is because these gas molecules are banging against the walls and banging against the diaphragm that's inside our pressure gauge. If they didn't do that, then we couldn't measure the pressure. All right. So those are different ways that we can express the pressure of a gas. the millimeters of mercury are based upon the barometer. I think his first name was Evangelista Torricelli. Is an Italian during the Renaissance. And they were really good in those days at blowing glass or making glass tubes of uniform diameter of any length you wanted. So Torricelli thought, in fact, I'm not sure what his thought processes were, but the end result was he had this pool of mercury. Okay, and he took this tube and he sealed off one end of it and filled it up with mercury. All right, so we had a tube here, closed at one end, opened, and he put mercury into it. All right, mercury liquid. And then he put his thumb over it and inverted it and submerged his hand and let go. Right, they didn't know about mercury toxicity back then. And when he did that, right, it was up here at the top. And when he did that, he noticed that the mercury dropped to this level. Okay, so just as an incidental, amaze your friends at parties. This was the first creation of a vacuum. In fact, they may have had to invent a word to describe it because it had something in that space. Now it doesn't. It's empty. So that's a vacuum. I think I need another marker. Let's see. Let's try blue. Okay, so Torricelli's reason that, well, first of all, it didn't stay at the top and it didn't go all the way to the bottom. So why is it being held up there? Well, there's nothing in here to suck on it, to pull it up, so it must be pushed up. So he reasoned that what was holding that column of mercury up was the atmosphere. Right? Air has mass, and it's pressing down on the surface of the mercury and transferring that pressure into the liquid and holding it up this high. So this difference at sea level, this is 1 atmosphere. And it's also 760 millimeters high. That's 1 atmosphere. Okay. So Torricelli, I don't know if he ran into this problem, but he could have used any liquid. You can't use a solid because it won't conform to the shape of the vessel. But he could have used any liquid. He could have used water. The problem with that is if he had used water to hold it 1 atmosphere high, the tube column would have had to been at least 33 feet high and probably more. So he chose a liquid that was more dense than water, and that was mercury. So mercury satisfied all the conditions required. And before we get to Boyle's law, one other thing that once a standardized way of measuring air pressure was developed and was made available to other scientists, particularly in Europe, they started playing around with them. Throw them in the back of your ox cart and go down into a depression below sea level. You're going to get a higher column because there's more air above you. Or if you go up on a mountain, it's going to decrease. Also, they set these things on their lab benches and just left them there. And every day they'd take a measurement. Okay. And pretty soon they were correlating a change in air pressure with weather. So we know that as the pressure is dropping, we're expecting bad weather to come. As the pressure increases, we're expecting good weather to come. And that's still true today. All right. So now let's get to our gas laws. We'll talk about Volume was already pretty well established. By the time Torricelli's barometer was invented, they knew how to measure volume. I don't know if they used SI units, but it was fairly standardized throughout the scientific community. Temperature came a little later, and then moles not too far behind temperature. So I'll describe the temperature standardization when we get to the law that requires it. But Boyle's law is going to be our first discussion. Boyle's law. What Robert Boyle, in the 17th century, I believe it was, did experiments using pressure and volume as the variables. And when you do that, whenever you let two of these vary and you want to see the relationship between them, you got to hold the other two constant. So for Boyle, he held the temperature constant and the number of moles constant. And what he found out was pressure times volume is a constant value. So if the pressure increases on your trapped gas, then the volume will decrease. That's an inverse relationship. Inverse relationship. Okay. Anytime you have the product of two variables equal to a constant, that's always inverse, because when one goes up, the other has to go down in order for that to be constant. The expression there, P1V1 equals P2V2, is for any given experiment, once you've trapped the gas, and let me back up. For Boyle, he used a J tube, let's see, like this. He just took a glass tube, sealed it one end, and bent it into a J. And then he started pouring mercury into it. And of course, it'd pool up on the bottom and get higher and higher. Once it touched that inner wall, this gas was trapped. Now we have that constant. And these experiments didn't take very long to perform, so the temperature didn't change in that amount of time. So once you've trapped them in there and you keep adding mercury, what he noticed was the height here of his mercury was not the same as the height here. Right? There's something pushing back against it. And this trapped gas has a certain volume, and the volume could be calculated because the diameter was uniform, and we know the volume of a cylinder, right, is height times area. So we could calculate the volume, or we could just say the volume is related to the height, right? So the height that this thing moves is a measure of the volume. Because you're going to use that same value over here, the height of the mercury column over here in millimeters is going to be the pressure plus atmospheric pressure. Two things are pressing down against that gas. One is the pressure of the atmosphere and the height of the column. Okay. So that's why when we do our experiment next week, you're going to measure the pressure against volume inside this device. You'll have to read about it. And we're not going to take just the pressure that's measured in the pressure container, but we have to add the atmospheric pressure because it's pressing against it also. So we have to get total pressure. Anyway, back to this one. Notice that for any pressure times volume, we get a constant. Once we started our experiment, if we add more mercury in there, then we increase the pressure. All right, so now we got a new pressure and we get a new volume, but that's still equal to the constant, the same constant. So we use the cumulative law, right? Mathematics. If A is equal to B and B is equal to C, then A is equal to C. So if these are both equal to K, then they have to be equal to each other. That's why P1 V1 equals P2 V2. That's a before and after situation. And it's like any equation. If you know these two conditions and one of these, you can solve for the other one. And that'll be the trend for any of these gas laws. If you know all but one, you can solve for it. Let's see. Is there going to be some more on Boyle's? Let me see before I erase that. This just is a hypothetical experiment. I keep dropping that cap. So if we increase the pressure, if we double the pressure, the volume is cut in half. So which of the following is the correct mathematical expression for Boyle's law? That's a good one. P1 V1 equals P2 V2. Or we can rearrange the equation. Just say P1 over P2 equals V1 V2 over V1. Or we could just solve for one of them and then plug in our values, and there you go. Okay, so for this exercise, I'm not sure if it's if I need to do it or if it's worked out for us. Okay. So if we have a sample of helium gas, and by the way, the nice thing about these early experiments with gases is that all the gases behaved alike. It didn't matter what the gas was. At these temperatures, room temperature and atmospheric pressure, a gas is a gas is a gas. So if we have 12.4 liters at 23 degrees Celsius, and the pressure inside is measured at 0.956 atmospheres, what volume will it occupy at 1.2 atmospheres? So let's see, the pressure is increasing, so the volume should decrease, assuming that the temperature stays constant. Right, so here we just filled in the values, and notice that when you use this type of arrangement, you've got a ratio. The P1 is ratio to P2 and the V1 is ratio to V2. So the units of measure, as long as they're the same on both sides, doesn't matter what they are. You can use any units you want. Atmospheres, millimeters of mercury, torr, pounds per square inch. They all work. And the unknown is going to be in the appropriate unit for its sister known value. So in fact, the volume did decrease from 12.4 to 9.88. Charles' law. Okay. Charles came along about a century later. He was in the 18th century. Charles was a Frenchman, I think. And the reason that these experiments were not conducted, volume versus temperature. See, this one's going to vary. This one has to be constant. And pressure has to be constant. To let that one vary with this one. The reason that Charles came along later was that there was not a standardized way of measuring temperature. So what we had was a series of inventions. One was by Fahrenheit. So we get our Fahrenheit system just from him. The other one was Celsius. Fahrenheit was working with living systems. So he wanted a temperature range that was roughly between normal body temperature and elevated temperature, or elevated temperature and cooler. So his range was 0 Fahrenheit was salt and ice. That's as cold as he could get the temperature. And 100 degrees was considered normal body temperature. So then he just divided it into 100 units. And within the tube that he was using was mercury. Okay, so Celsius came along. Celsius was interested in chemistry, pure chemistry rather than biology. So his system was also 0 to 100, but he wanted convenient ways to calibrate thermometers. 0 degrees for Celsius was freezing point of water. And 100 degrees was boiling point of water. So any lab anywhere on the planet could calibrate their thermometers using these values, and he divided 100. Okay. Now, if you want to convert backwards and forwards between the two, you've got two problems. The 0 point is different. So we got to shift the 0 point to get that right. But the size of the degrees is also different. So the size of the degree in Fahrenheit is about half of the size of the degree in Celsius. So when we set up our conversion from one to the other, this is the one I memorized. So Fahrenheit temperature is 5/9 of Celsius plus 32. This is also, oh, excuse me, that's not right. 9/5. Sorry, it's 1.8. You may see it in textbooks. The other system was invented by Lord Kelvin. And what he wanted was to do thermodynamic calculations without having the inconvenience of negative temperatures. Either one of these systems, it will have negative temperatures at some point. You'll go below 0 here, below 0 there. Kelvin wanted all positives. That eliminated the problems with negatives and positives. So he proposed an absolute system where 0 was absolute 0, nothing colder, 0 K. And notice we don't say 0 K. We don't say degrees K, we just say K. All right, so the short version is, if you want to know the Kelvin temperature, you take the Celsius temperature plus 273. That's what that means. There's more to the story. How did he come up with that? And in the interest of time, we'll have to skip that right now. If it shows up later, if I have it in another slide, we'll talk about it. Oh, by the way, Charles' law can be expressed this way: volume temperature equals K. So this is a direct proportion. In other words, as volume goes up, temperature goes up. Anytime you see a quotient of two variables equal to a constant, it's always a direct proportion. And just to beat the dead horse again, anytime you have a product of two variables equal to a constant, that's an inverse proportion. I'm going to have to get a fresh marker. Here we go. All right. So, and by the same token, since this is equal to a constant, 1 and 1, then V2 and T2 is also equal to that constant. So they're equal to each other. We use the same reasoning, and we have a before and after situation. V1, T1 equals V2 over T2. Now you might wonder if constant number of moles is easy. Once you trap the gas and don't put any more in there or take any out, you're good. And there's no chemical reaction. Right? That'll change the number of moles too. But how do we keep a constant pressure? Well, you just need a piston, a movable piston with set of mass on top of it, like 1 kilogram. And the pressure is going to be constant all the way through the experiment. All right. So if we have a balloon that contains 1.3 liters of gas, and by the way, a gas is a gas is a gas, at 24.7 degrees Celsius, placed in a beaker containing liquid nitrogen at minus 78.5 degrees Celsius, what will the volume of the sample of air become at constant pressure? Let me take a closer look at that, because that's not liquid nitrogen. That's an error. Liquid nitrogen is a lot colder than that. Let me mark it so I can fix it later. Here we go. Actually, this is dry ice. Dry ice, solid carbon dioxide becomes solid at minus 78.5 degrees Celsius. Liquid nitrogen is minus 195 degrees Celsius. So let's stick with the numbers we have. Just recognize that this is not liquid nitrogen. But here we have that negative temperature, right? If you put negative temperature into this equation, right? If this one is, 24.7 degrees C, and this one is negative 78.5 degrees C, you're going to come out with a negative answer, right? You can't have a negative volume. So when we're dealing with gas equations, you've got to change your temperature to Kelvin. We got to add 273 to that. We add 273 to this one. Now we got all positive values. And once we've done that, right, we can plug them into the equation and determine that the new volume is, in fact, less than the original at 0.849 liters. It decreased from 1.3. All right. That was Charles' law. All right. We left out. Okay. We left out Avogadro's law. Avogadro came along not too long after Charles. And Avogadro's law, let's see, without a lot of backstory, Avogadro's law says that the volume varies with the number of moles is equal to a constant. So in order for that one to work, temperature and pressure, I should erase that one, these have to be constant. Oops. Temperature and pressure constant. To let this one vary with that one. And that just says, if you've got a combined gas with the temperature that's constant, the pressure is a constant, and you put more gas in it, then the volume is going to increase. Okay. So now that we have that one, we can move to the combined law. And these are all before and after conditions. In other words, I can say V1 over N1 equals V2 over N2 also. But the combined gas law is going to look something like this. All right, so if we have P and V times one another, is equal to P2 V2. Right, that's true. What's the relationship of volume and temperature? Well, V1 over T1 equals V2 over T2. Okay? And V1 over N1 equals V2 over N2. So this is a combined gas law where we have P1 V1 over N1 T1 equals P2 V2 over N2 T2. That way, if we have a before and after situation where we're given some values and only one of them is missing, we can solve it. Now, in the slide, of course, we left out the number of moles. That's what clued me into a problem. And also remember that these temperatures must be converted to Kelvin. All right. So in this case, at what temperature does 121 milliliters of carbon dioxide at 27 degrees and 1.05 atmospheres occupy a volume of 293 milliliters at a pressure of 1.4 atmospheres? When you have word problems like that, in order to get them in the right place in your formula, it's probably a good idea to set up a little table. All right, so we're going to have P1, V1, T1, and this gas is confined, so the number of moles goes out. We won't have a number of moles. And then P2, V2, T2. All right, it's asking us at what temperature. So this one is going to be unknown. The second temperature is unknown. First temperature is 27 degrees Celsius. So we have to add 273 to it. The first pressure is 1.05 atmospheres. And the volume, the first volume is 121 milliliters. Okay. The final pressure, final volume is 293. No, wait a minute. I marked the wrong one here. This one is unknown. The final volume is 293 milliliters. And the final pressure is 1.4 atmospheres. Okay. So if we plug that into our formula and solve for the unknown temperature, we should get it here, is 969 K. Remember, the temperature is going to be in the same units here and here. So we have to subtract 273 in order to find out what the Celsius temperature is. 696 degrees C. Okay. That little trick, that's not a trick, it's logical. Set up a table and put the numbers where they're supposed to be. Then when you plug them in your equation, they'll go in the right place. All right. Now, all of these that we've discussed before are before and after situations. If you know the conditions before and know all but one of the conditions after, you can solve it. But there are some problems that are presented to us in the form of what are the conditions right now? A state function. What are they now? Solve the problem. Right? So we're going to use the combined gas law and reason this one out. Right? So there we have that. All right. So this is before, this is after, but they're still both equal to a constant. Right? So let's do away with this one for now and just keep the constant, because this is going to be our situation. We're at this position, one of these is unknown. So how do we find it? Well, the trick is, what is that value? If we know that value, then we can solve for it. So in order to have a known, Butterfingers, in order to have a known value for constant, we have to have also standard units. Right. So if we let this one be atmospheres, this one equals liters, this one is moles, and this one is K, temperature. Then the units of measure here are liter atmospheres per mole K. And if we let this be 1 atmosphere, this is 1 mole, this is 273 K, which is 0 degrees Celsius, which is standard temperature for all gases. Then what's the volume? Well, we have to measure the volume. And the volume turns out to be 22.4 liters. If we have all those values in there now, we can calculate this value to be 0.08206 liter atmospheres per mole K. And this is given a special symbol, R. Okay. Now, the danger here is that you plug in the wrong units for these. Since this constant has a set unit structure, liter atmospheres mole K, then these values also have to be liters, atmospheres, moles, and K. So if you're given a problem where the pressure is something else, then you got to convert it to atmosphere. Or where it's a different volume, then you got to be sure it's in liters before you can use this constant. Okay, normally we see this equation written this way, PV equals nRT, which just rearranges things. All right. So here's one. If your automobile tire is at 23 degrees C with an internal volume of 25 liters, is filled with air to a total pressure of 2.18 atmospheres, determine the number of moles of air in the tire. So let's see, we have liters? Yep. We have atmospheres? Yep. We have moles? No, we want to determine the number of moles, and we have temperature. 23 degrees has to be converted to Kelvin. If we do that, then we can plug them into the formula and determine that the number of moles is 2.24 moles of gas in that tire. Now, this is a state situation versus a before and after. Here's another possibility. So in this case, we know what the gas is. 5.670 kilograms of helium in a 304 liter tank. And we want to know the pressure at 25 degrees C. So in this one, we say pressure, volume, moles, temperature. Right? We want to know the pressure. Right? So we have to, that's a question. 304 liters. Okay. That's in the right units. Moles. We don't know the moles. We know kilograms. So it's 5.670 kilograms of helium. And 25 degrees C. That's plus 273. Okay, so we got to convert this to moles. Remember how to do that? Dimensional analysis has to make grams first. So 10 to the third grams per kilogram. Okay, then we have to convert grams to moles. So for helium, it's about 4. So this number times 1,000 divided by 4 equals the number of moles. And once we got the moles, volume, temperature, and the value of R, then we can plug it into that formula and find out what is the pressure. And that's what we've done there. At 114 atmospheres. Okay. More laws. Remember John Dalton? We talked about him early on. with the atomic theory, Dalton's atomic theory. Well, that's not all he did. He worked with gases too. And he came up with this one, which is extremely useful. Dalton's law of partial pressure. Partial pressure. What Dalton said was that when you measure the total pressure of a mixture of gases, it is that pressure because each one of those individual gases exerts its own pressure. Okay. Very simple, right? But we can expand it because we know that the pressure in the container is also related to the number of moles. And that's from the combined gas equation, right? If we say that PV over NT equals a constant, then if the pressure goes up, and we hold volume and temperature constant, then it's due to the number of moles. Right? So the number of moles here also is related. Okay. So if we have a gas mixture of oxygen, helium, nitrogen, total pressure of 780 millimeters, what's the partial pressure of oxygen if the partial pressure of helium and nitrogen are 86 and 124 respectively? Well, we know that the total, those three totals, have to add up to that one. So we've just got an equation with one missing, one unknown. We can solve it. And it turns out to be 570 millimeters of mercury. Okay. So let's take this problem, see if we can use Dalton's law to solve it. So we've got two cylinders. We got one that's what, 9 liters. We have 9 liters over here, connected with a valve to another cylinder that's only 3 liters. So we have 3 liter volume here. We have a 9 liter volume here. And they're both filled with gases. This one is at a pressure of 2 atmospheres. And this one's at a pressure of 3 atmospheres. Okay. All right, so what's the final pressure? What would be the final pressure if we open that valve? We can look at it first as a semi-quantitative. Can the pressure be higher than 2 or higher than 3? No, it's got to be in between somewhere. Okay, so once these two gases mix, what's going to be the total pressure? The total pressure, let's see, they tell us what the gases are? No, they just say 1. So let's say this one is P1 and this one's P2. So the total pressure is going to be P1 plus P2. So what we have to do is find out what will be the pressure of P1 that occupies that new volume. That sounds like a Boyle's law problem. Pressure volume is constant. Okay. And we could do the same thing with the other side. So how do we do that? How do we keep them separate? Well, we use a little mind trick. We say, okay, that's a vacuum. If we open that valve and let that gas expand into this vacuum, what's its new pressure? And then we say, okay, back up, make that a vacuum. Let this one expand into that vacuum. What's its new pressure? Well, the pressure now that's exerted by this gas plus the pressure that's exerted by that gas is the total. So once we find the individual pressures, we can add them together. Right? So this is going to be P1 V1 equals P2 V2. And pressure 1 is 2 atmospheres. Volume 1 is 9 liters. Pressure 2 is our unknown. And volume 2 is now what? 9 plus 3 is 12 liters. Okay, so P2 is going to be equal to 2 times 9 is 18. 18 divided by 12. All right, so that's 9/6, or wait a minute, did I do right? 12 into 18. Let me just take the easy route. 1.5 atmospheres. Okay, we do the same thing on this side. What was P1 over here? P1 was 3 atmospheres. And volume 1 is 3 liters. Okay, now we're going to have P2 for this one, where that one's a vacuum, times the new volume, which is 12. Right? So P2 equals 9 divided by 12, or 1/3, right? 0.33. No, 6/7. Let me do it. 9 divided by 12. 7.5. Can't do it in my head anymore. Okay, so now the total is 1.5 plus 0.75. 2.25. Right? And we estimated it would be between 2 and 3, and it is. So we used actually 2 laws. We used Dalton's law of partial pressures and Boyle's law to solve this problem. Oh, we've got slides doing it too. Okay, so there's one side, and there's the other side, and there's the total. Where we're going. This will be 7.1 to 7.8. And now we're going to go 7.9 to the end of the chapter. Oh, probably this evening. Okay. Yeah. All right. That solubility chart, the one with the gray boxes on it, we're not going to use that one until next chapter 8. Okay. Okay, change of state. It's simply the process describing the process in which a substance is transformed from one physical state to another, like from a liquid to a gas, or a liquid to a solid, or in fact, a solid to a gas, or a gas to a solid. If we put this in a visual form, the authors have a nice little diagram, but I'm going to draw one of my own. If, say, we have a gas here, that's the gas state, and we have a liquid state over here, and we have the solid state over here. Okay, if we go from a liquid to a gas, you know what that's called, right? That's called evaporation. Okay, if we go from a gas to a liquid, that's called condensation. Okay, if we go from a solid to a liquid, that's called melting. And if we go from a liquid to a solid, that's called freezing. Okay, now here's the special one. Gas and solid, direct transfer from one to the other. Okay, if we go from a gas to a solid, that's called deposition. And if we go from a solid to a gas, that's called sublimation. Okay. Everybody knows sublimation. Just take a chunk of dry ice and lay it out on the bench top or out on the pavement on a hot day, and you'll see it shrink as it converts directly from solid to gas. That's sublimation. That's why they call it dry ice, because it doesn't make a liquid. It doesn't get your products wet. So there are all the terms that we just discussed. Let's see, freezing, condensation, deposition, melting, evaporation. Yep, they're all there. And this came out of your textbook. And you see, the reason I drew it this way is because I like mine better. What this one does add is the heat transfer that's required for each of these changes. Okay, so we can superimpose that upon this one. If we go from a liquid to a gas, you have to put heat into it. And the proper term for that is endothermic. Heat has to be absorbed by the liquid to make it into a gas. Endo means into, and thermic means heat. Heat goes into the substance to make the gas. If we're going from solid to liquid, it's also endothermic. We're increasing the temperature. Well, actually, we don't. All these processes occur at constant temperature, but we're putting energy in to change the solid to the liquid. In other words, we're increasing the kinetic energy so that it overwhelms the cohesive forces. And if we go from gas to solid, let's see, solid to liquid, solid to gas, sublimation. This is also endothermic. You got to put energy into the solid to turn it into a gas. That means that all the processes in the opposite direction are exothermic. They will give up heat in the process. So condensation is exothermic. Deposition is exothermic. And freezing is exothermic. Now, the terminology they use here is heat released, heat absorbed, which is the same thing, but this is the proper terminology for the physical process that takes place. Okay, that just restates what I put up here, so I'm not going to spend a lot of time on that one. Also this one. All right. So if we look at these in terms of that cohesive versus disruptive forces, anytime you go from, say, a liquid to a gas, or a solid to a liquid, or a solid to a gas, the disruptive forces, the additional kinetic energy, is there to overwhelm the cohesive forces. So evaporation is one example of that. When you go from a liquid to a gas, you put energy into it, it's endothermic, which makes the kinetic energy increase, temperature increases, well, not temperature, but kinetic energy increases, and you change state. Okay, as liquids evaporate, we can say something about the rate of evaporation. If we take a liquid and rapidly increase the temperature to a certain level, it will evaporate more quickly because there's more energy available. So if you put a drop of water on your hand in the summer, it will evaporate and you'll feel your hand get cold as the heat is transferred endothermically from your hand into the water. And it'll take it a while, but eventually it'll evaporate. Or you can take that same drop of water and you can heat up a stovetop, say a ceramic stovetop. You can get the eye really hot and then drop the water on it and it'll go and be gone in seconds. So the difference in temperature there was the cause for the rapid evaporation. This gas phase is often referred to as a vapor. And the reason we want to identify that term is because we're going to discuss a physical property of gases. Different gases exert different vapor pressures in a closed container based upon what liquid it is that is evaporating and the temperature. So we'll come back to that term. Okay, so here in a closed container, we're going to talk about evaporation. You got this liquid, and you got a cork in it, and your liquid is here, and it's evaporating. Okay, that's the first thing that happens. When you cork that bottle, the evaporation continues. We assume that there is essentially nothing in this space above. So you've got liquid molecules from the liquid leaving the surface of the liquid and becoming a vapor or a gas. Now, at some point, you get enough of these up here with sufficient pressure so that they start returning. So you get condensation. Okay, so at some point, and you notice that in this diagram, the liquid level is dropping as we get more and more of that liquid into the vapor phase. At some point, this evaporation rate is equal to the condensation rate. And at that point, the level of the liquid stops dropping. It doesn't change anymore. So that's what we see. The macroscopic evidence is that the liquid doesn't, the liquid volume does not decrease any further. But there's something else that also remains constant. When this rate, evaporation and condensation, these two are equal, there is a pressure up here. We could put a gauge in it and measure the pressure. And that pressure would be constant at a temperature. But on the microscopic level, what's happening is these two rates are equal, they're balanced. And at this point, we have what we call physical equilibrium. Both rates are occurring. We don't see any further change in the liquid level. Pressure is constant. That is a physical equilibrium. And this vapor pressure is dependent upon two things. It's dependent upon the temperature and the nature of the substance. So water at a given temperature will have a certain vapor pressure. Ether, right? Diethyl ether, the same stuff they used to use to put you to sleep for an operation. The ether, if you put ether in there instead of water, the vapor pressure would be much, much higher at that same temperature. Now, the explanation for that is cohesive forces holding those water molecules in the liquid phase are very strong, whereas the cohesive forces that are holding the ether in the liquid phase are very weak. So if the forces of cohesion are very weak, then at the same temperature, there is sufficient kinetic energy to put more of those ether molecules in the vapor phase than there is for the water. So the weaker the cohesive forces between the molecules, the higher the vapor pressure. Sometimes we refer to these as volatile substances, those that produce relatively high vapor pressures for a given temperature. And here the example is this molecule right here is dimethyl ether. Anytime you have an oxygen in the middle and two groups on the outside, that is an ether. You can also reference, say on the, if you look at a can of paint, somewhere on that label, it will have to say what is the volatile organic compound content, VOC, content of that can. The EPA dictates that part of the label. And for those that have these types of volatile compounds, the VOC is going to be high, whereas the water-based paints are going to be very low. That's why water-based paints are generally preferred. Okay. So boiling. Evaporation. Okay. Boiling is a special term for evaporation. Boiling is evaporation at 1 atmosphere pressure, or boiling at a constant pressure, where you turn the liquid into gas inside the liquid itself because the pressure on the surface is low enough. And the internal kinetic energy, the disruptive forces, is high enough. So the authors are saying boiling is a form of evaporation, which is true, where conversion from the liquid state to the vapor state occurs within the body of the liquid. That's why you see bubbles forming. And you generally see the bubbles forming at the heat source, right? So if you put a pan of water on the stove, you're going to see the boiling occur at the bottom of the pan, at the bottom of the liquid. So that's where the heat's being delivered. Boiling occurs when the vapor pressure of the liquid at that given temperature reaches a value that's equal to the external pressure on the surface of the liquid. So it'll be a certain boiling point at 1 atmosphere pressure, sea level. It'll be a different boiling point at half a mile high, which is where I live. Beckley is about 2,500 feet. And it'll be even lower at Denver, which is a mile high, 5,000 feet. So you decrease the external pressure and the liquid will boil at a lower temperature. That's why a 3-minute egg in Denver is probably 4 minutes or 4.5 minutes, because you can't get the water as hot. It'll boil and it'll stay at that temperature until all the water's gone. That's another characteristic of these phase changes. The phase changes occur at a constant temperature. So if it boils at a temperature at sea level, it'll boil at a lower temperature in Denver. That means with lower temperature, the boiled egg has to be kept at that lower temperature for a longer period of time. So there's boiling. By the way, when you first put a pot of water on the stove and heat it up, the first bubbles that you see are not water vapor. The first bubbles that you see are dissolved gases inside the liquid that are coming out with increased temperature. Once those are all gone, it may stop producing bubbles for a little while, and then once it reaches its boiling point, then you get the water vapor coming out. So when we say normal boiling point, we're saying at what temperature does the liquid boil at 1 atmosphere pressure? And there's why the boiling point changes with atmosphere, with elevation. Just like I described it a minute ago. Okay, and here we have, let's see, New York City is virtually sea level. So the boiling point of water is 100 degrees. Death Valley is going to be a little higher because it's below sea level. Wisconsin, a little bit less. But if you go all the way up to the top of Mount Everest, water is going to boil at 70 degrees Celsius. 30 degrees lower temperature will boil water at the top of the world. All right. What's the vapor pressure of water at 100 degrees C if it's boiling at that temperature? We know that water boils at 100 degrees C only when the external pressure is 1 atmosphere. So the vapor pressure of water at that temperature, if it's boiling, is 1 atmosphere. Okay. So we talked about disruptive versus cohesive forces earlier. These cohesive forces are what are also identified as intermolecular forces. That is, for instance, 2 water molecules approach one another. And we've already talked about the polarity of the water molecule. This is going to be slightly positive. This is going to be slightly negative. So if another water molecule approaches such that the negative is close to the positive, we get an electrostatic attraction between the two. That's an intermolecular force. And that occurs in liquids, it occurs in solids, it occurs in gases. Not so much in gases because of the reasons we've described earlier. This is opposed to intramolecular forces. The intramolecular force when we say intramolecular, we're talking about bonds within the molecule. Right. These are intramolecular forces, those bonds between atoms. Intermolecular are between separate molecules. Now, relatively speaking, these bonds are much, much greater than intermolecular. These are going to be greater than intermolecular forces. And it just makes sense. If the intramolecular forces were weaker than the intermolecular forces, then when a molecule approached another molecule, they just rip each other apart because these forces of attraction would be so much greater than the intramolecular forces, they'd overcome the bonds. So if the molecule is going to stay intact, then the intramolecular forces, the bonding, must be greater than the intermolecular forces. Maybe I didn't describe this before. All right. I was thinking we did when we talked about Yeah, when we talked about the bonds. All right, so this is going to be partially a review. Let me make some room here. Don't erase my squares there, my rhomboids. Okay. So when we order these intermolecular forces in order of strength, we find that the ion-ion interactions are the strongest. So we have two ions together. They're the strongest. The next strongest would be ion dipoles. So where would you get an ion? An ion-ion interaction would be like solid sodium chloride. Right? We know that the bonds are strong because in order to melt sodium chloride, you've got to get it really, really hot, 1,000 degrees or more. But the ion dipole interactions can occur at much lower temperatures, and you can put that salt you put into solution, then you get the dipole of water interacting with the ions of the salt. That's a little bit weaker. Okay. Then if you have a solvent, that's a dipole, and a solute, that's a dipole. For instance, water and sugar, those are a little bit weaker forces. Now, stuck in here is a special kind of dipole-dipole called a hydrogen bond. In fact, this is an example of a hydrogen bond. In order to have a hydrogen bond, you need an electronegative atom like nitrogen, oxygen, or fluorine. And then you have bound to that hydrogen. And you can have something else over here. But this is such a difference between electronegativities that you get a very strong attraction, very strong dipole here. And the hydrogen bond then occurs between molecules that have this arrangement. So for water molecules, that's a perfect example of a dipole of a hydrogen bond. This is a hydrogen bond. And it is the strongest of the dipole-dipole interactions. Okay? Now you can get dipoles without dipole-dipole interactions without the hydrogen bonding. But when you have the hydrogen bonding available, that is the strongest of the dipole-dipoles. Then we have one that's very, very weak. It's called London dispersion. London dispersion forces. How do we know that they exist if they're so weak? Well, in fact, they exist all the time. They're always there. Even with these dipole interactions, the Londons are always there. If these are present, then they're so strong they overwhelm the London dispersion forces, and we don't need to consider them. But if we don't have the dipole-dipole available, for instance, if we have nitrogen gas, right, like that, and we cool it down so that the disruptive forces are minimized, then the cohesive forces take over. Well, what possible cohesive forces could there be? There's no dipole here because these are exactly alike. So what is it that holds them together when they condense into a liquid at minus 195 degrees Celsius? The explanation is London dispersion forces. So these are characterized by the fact that they're temporary and they're very weak. Okay, so what I mean by temporary, the electron density in a molecule is not static. It is dynamic. It's changing constantly. So you can get, in a split second, you can get a slight negative on this side and a slight positive on that side. It only occurs for a split second, then it's gone. But while it's there, it can influence its neighbors. So if we have another nitrogen here, this negative tends to repel electrons, and this positive tends to attract electrons. So now we get a negative here and a positive there, right? Repulsion, attraction. So in that split second, you can get attractive forces between the molecules. That's why at 195 degrees Celsius below zero, we can turn that gas into a liquid, because now those very weak cohesive forces are strong enough to condense the gas into a liquid now, because we have minimized the kinetic disruptive forces. What we see here is that the London dispersions are always there, and they tend to increase in significance, in strength, as the molecule gets bigger. Because with bigger molecules, you have more physical room to redistribute electron density over that period of time. And you also have more places upon the molecules that can attract one another. Okay. So this dipole-dipole interaction I've described before depends upon the polarity of the molecules. If you have polar molecules, you will have dipole-dipole interactions. And here is a molecule of fluorine and chlorine. Fluorine is a stronger, more electronegative atom, which draws electron density toward itself, making the chlorine side a little positive and the fluorine side a little negative. And then the orientation will give you a dipole-dipole bonding, an intermolecular force. This reiterates what I said about hydrogen bonds. It's a type of dipole-dipole, but it requires that you have either fluorine, oxygen, or nitrogen attached to a hydrogen. Now, when you can have hydrogen bonding on very large molecules where they bond with other portions of a molecule, if it's big enough to where it can wrap around, or you can have things like this. You can have right? So you can have a dipole set up here on this ethanol molecule, right? The drinking kind, ethanol, ethyl alcohol, and it will be attracted to other ethyl alcohol molecules, or it can be attracted to some other things like water. But you can have these hydrogen bonds formed in different places around the molecule. For instance, glucose, right, that circulates in your blood to deliver energy to different cells, is shaped like this, right? It's a hexagonal shape. And let's see, right? So you've got a hydrogen bond here. You have the potential for for more hydrogen bonds here, like that. So we've got hydrogen bonds scattered all over that molecule. Glucose is a member of sucrose molecule. So sucrose just adds another one out here, but it's got all these OHs on it, and you can put it in aqueous solution to the extent to where you have more sucrose in the solution than you do water. That's how strong these bonds are. So this is just rehashing. Why is the hydrogen bond so strong? Well, the highly electronegative elements that are bound to the hydrogen shift the polarity of the bond extremely toward the electronegative atom, like oxygen, fluorine, or nitrogen. And because the hydrogen atom is so small, then you can get these things in here very close. Right, you can get the water molecule in there very close like that. Because this is extremely small, the strength of the bond is determined by two things. The charge or partial charge on the atom and how close you can get to it, right? It's just like gravity, right? Big things have big gravity, and the closer you get to them, the stronger the force. Same thing with electrostatics. Okay, there's hydrogen bonding in water. The vapor pressure of liquids that have significant hydrogen bonding is much lower. I mentioned that earlier with water. The hydrogen bonding is there with water, so the vapor pressure is very low. But let me give you an example. Not just water, but let's say we have two molecules. Let's see, C2. Let's see, 3, 5, like that. We have this molecule, the formula, C2H5O. We can draw that formula like this, CH3, CH2, OH. Let's see, that's O6. 6. 3 hydrogens, 6 hydrogens, oxygen, 2. Okay, we can draw it like that, or we can draw it like this. It's the same formula, but different structure. In this one, we have hydrogen bonding. In this one, we don't. The vapor pressure of this one is much, much, much greater than the vapor pressure of that one, because this one has hydrogen bonding and that one does not. Okay, so in this one, we're trying to explain why water does not follow the trend, right? These tellurium, selenium, sulfur, and oxygen are all in the same group 5A, and we're forming hydrogen, dihydrogen molecules with each one of these elements. If water followed the trend, it would be a decreasing boiling point, right? From -2 here to -41, -60. It should be down here around -80, but it's not. Water has a very high boiling point because now we're moving up in the family, in the group, and the electronegativities are increasing so that we get to a point where oxygen has a very high electronegativity, which makes for extremely polar bond with hydrogen. And that we get the hydrogen bonding, and that's why this anomaly exists, where you get hydrogen, water, have a very high boiling point. And actually, it's fortunate for us that it does, because this is a water planet. And if it were not for this fact, then there would be no liquid water on the surface of the Earth. It would all be evaporated, boil away. London forces, I described those earlier, so we don't have to spend a lot of time on this one. They're weak and they're temporary. And they can occur between polar molecules and nonpolar molecules. They can occur between atoms and molecules. They're always there. Whether or not they're significant is the question. If there are other forces, like ionic forces, dipoles, interactions, hydrogen bonds even, then those are usually so strong that the dipole forces are insignificant and can be ignored. All right. So here is let's focus on the noble gases. All right. These are in order from top to bottom as they occur in the periodic table. So as we go from helium down to radon, the atoms are getting bigger. Okay. As they increase in size, we have more room to redistribute electron density. So that means that we can sustain temporary partial charges for longer periods of time around the larger atoms. So that means that the boiling point should increase as we get bigger atoms. And in fact, it does. As we go from helium down to radon, we notice that the boiling point increases from minus 269 degrees C all the way up to minus 62 for radon. Notice that this helium, minus 269, is equal to 4K. That is the coldest substance that we can produce in the laboratory and maintain and hold it. Liquid helium is 4K. It's really a weird substance. If you ever have a chance to look at video of it, I've seen it up close and personal. Liquid helium in a thermos, they call them a Dewar flask. Right? Just like a thermos bottle, it's silvered, and there's a vacuum between the two containers. But if you open the top, that liquid helium is going to start climbing the walls, and it'll climb its way out of the container. It's the strangest thing I ever saw in my life. The liquid will climb its way out. Okay. So this is just a check. Intramolecular bonds, are they stronger than intermolecular? Yes, they are. How do we know? Because if it were not the case, molecules, when they approached one another, the intermolecular forces would rip them apart. So which one of these has the stronger intermolecular force? Think about polarity. The nitrogen molecule is nonpolar. The water molecule is extremely polar. In fact, it has available to it hydrogen bonds. So the stronger intermolecular forces are associated with water. And there's your explanation. How do we know? The difference in boiling point is a good place to start. Right? Water boils at 100 degrees Celsius. Nitrogen boils at minus 195 degrees Celsius. That's a difference of 295 degrees in their boiling points. Oh, here's the example I showed you earlier, right? Same formula, different structure. Ethanol has hydrogen bonding available. Dimethyl ether does not. So dimethyl ether has a lower boiling point and a higher vapor pressure because it's nonpolar. Okay. So what do we mean by ideal behavior in a gas? Ideal behavior is a gas is a behavior in which the gas behaves as if it were not even there. In other words, we can compress the gas and cool it, and it will stay a gas all the way down until there's no volume there. Okay? That's ideal behavior. Now, under what conditions do gases behave ideally? They behave ideally when the cohesive forces are virtually zero. Remember earlier when we talked about disruptive and cohesive forces? If the cohesive forces are near zero, by comparison to the disruptive forces, then they will behave ideally. So when does that occur? Well, that occurs when there is little or no interaction, attractive forces between the molecules, and when the disruptive forces are high enough to overcome any interactions or cohesive forces that may exist. Right? So in this example, what we're looking at is a difference between carbon monoxide and nitrogen. So if we compare them, right? What we see is oxygen is more electronegative than carbon. So we have a dipole set up here, whereas this is nonpolar. So the one that has the least intermolecular interaction is going to be more ideal, which is nitrogen. Now, let me see. I'm going to check to see if it's included here. No, I will make a point though. Ideal behavior. Ideal gas behavior. All right. Under what circumstances? Where we have low, well, actually, ideal behavior means no intermolecular forces. 2, high temperature, right? And that room temperature satisfies that condition. This is the disruptive force. And 3, low pressure. And corollary to that is low moles. Ideal behavior also occurs when there's not much gas there, right? Which means you have fewer molecules to interact. So there's more ideal behavior. So low pressure, high temperature, and no intermolecular interactions means ideal behavior. Okay. I'll leave that up for just a few seconds so we can get it recorded. And make room for any new stuff. All right. Oh, we must be near the end. We got our concept questions here. All right. let's see, what does it say? To hide some helium-filled balloons for a birthday party, you decide to place them in a chest freezer. When you retrieve them, this is like one of those big freezers where you have to open the top. When you retrieve them, you find that the balloons are deflated, right? That makes sense, right? Charles' law says, decrease the temperature, decrease the volume. As they warm up to room temperature, they return to their original size, okay? What gas law is demonstrated in this scenario? I just told you, Charles' law. So it's either C or D. What happens to the kinetic energy of the helium during the warming process? The kinetic energy increases because the temperature increases. Remember, temperature is a measure of the average kinetic energy of all the molecules in a substance. So the last one satisfies both of those conditions. All right. This one might take a little work. So let's make some room just in case. All right. Check yourself. A gas water displacement experiment is set up, and it's determined that, okay, what is a gas water displacement experiment? Let me draw you a picture. So we have a reaction vessel over here. So there's a reaction that's going to occur here and produces a gas that we want to capture. So we take that gas and we run it through tubing here, and it goes inside a container of water. Then it bubbles up the water, okay? But we want to catch it. So what we have is a graduated cylinder right? That's got volume markings on it. And it's filled with water all the way to the top or the bottom, as the case may be. And it's been inverted here, right? So as the gas accumulates up here, we get it. It's filling the space. And eventually the reaction is complete. And we have this much here, gas, plus what? Water vapor. Right? We got both of them in there because we've bubbled the gas through water, so it's going to accumulate some water vapor. But now we are able to capture the gas and measure its volume. Well, actually, we're measuring the volume of both the gas and the water vapor. So there's the problem. All right, so now conditions. We have 0.812 grams of gas. So 0.812 grams of the gas displaces 350 milliliters of water. So this volume okay. The atmospheric pressure is 750 millimeters of mercury. Right. So pressure is 750 millimeters of mercury. All right. Temperature of the water is 20 degrees. 20 degrees C. And the partial pressure of water is 18 millimeters of mercury. So the partial pressure here equals 18 millimeters of mercury. Right there. Okay. What's the molar mass of the gas using the ideal gas law? All right. What we need what do we need to determine to find the molar mass of the gas? Molecular weight, that's my abbreviation for molar mass, is mass of the gas but per mole, mass per mole, right? So we got the mass already right here, 0.812 grams. What we need is the number of moles, right? So that's why they said use the ideal gas equation, right? PV equals nRT, so N equals PV over RT, right? So we need the pressure of this gas right here. In our first term, we need the pressure of that gas. So if this is the total pressure, if total pressure equals the pressure of the gas plus the pressure of water vapor, then the total pressure is 750 millimeters of mercury. Pressure of the gas is unknown, and the pressure of the water is 18 millimeters of mercury. So the pressure of the gas equals 750 minus 18, or 237. Okay, millimeters of mercury. But we can't use that in that equation because it's not atmospheres. So we got to convert it to atmospheres. So 732 divided by 760 equals how many atmospheres? Does that make sense? Right? 732 is less than 760. So it should be a division. 732, 760 is 0.9632. 0.9632 atmospheres. That's the pressure of the gas. So now we can start filling in our values. Pressure of the gas is 0.9632 atmospheres. Okay, what's the volume? Well, the volume is the same for both gases, 350 milliliters, which is how many liters? 0.350. 0.350 liters. Okay, what's R? We know that one, 0.08206 liter atmospheres per mole. Okay, and what's the temperature? The temperature is 20 degrees. So what's that in K? 20 plus 273 is 293 K. 293 K. There we go. So now we can solve for the number of moles. 0.9632 is already in there. 0.35. I better do that again. 0.9632. I hit the wrong key. 0.35. 0.08206 divided into that, and 293 divided into that. So if I did it right, let me do it again. Yeah, okay. 0.014. 0.014 moles. So now we can do the calculation. 0.014 moles. Right? Isn't that right? Grams per mole. So 0.812. 57.9 grams per mole. I'll round it off to 58. Oh, I got an animation showing you. Okay. There's what we're given, all that information. So now we're going to find out that's how many millimeters of mercury is for the gas and with water subtracted. And that converts to that many atmospheres, right? And then we use that equation to calculate moles. There we go. And plug it in the There it is. 0.812 divided by that many moles is 58 grams per mole. So there you have it. Okay, I think that's the last slide. Yes. So let me stop the share. And that is chapter 7, gases, liquids, and solids. Chapter 8 will be solutions. So we'll talk about solutions next Monday and follow it with the Boyle's Law lab. So be sure and read the lab. Be ready to come to class. It's a really simple lab, but it does have some hazards. We have a pressure vessel that is basically a 2-liter pop bottle. And we use them once and destroy them, throw them away. We don't stress them and use them again because eventually they'll overstress and pop. So come prepared, and we'll see you next Friday for chapter 8 and Boyle's Law.